Okay, so let's continue to look at some examples of proving things by contrapositive. Here we're going to look at um, an exercise from the book. This is exercise 6.4. And the implication is that we're going to prove is that if m times n is odd, then m is odd and n is odd. Again, the Q part of the implication is an and, so when we go to write down the contrapositive here, we have to remember that when we take not Q, we're going to get that m is even and n is even, but the and becomes an or, right? So if m is even or n is even, then m times n is even. Okay, so we're using the fact that when you not, the and, so let's just say a and b, where a and b are two expressions, then that's equivalent to um, not a or not b, right? So we've seen that logical equivalence in the last chapter, and that's what we're using here when we compute the um, contrapositive. And now we're going to prove this P implies Q. We're going to prove that if m times n is odd, then m is odd and n is odd. But we're going to do this by contrapositive, right? So assume that m and n are integers, and we want to show that if m times n is odd, then m is odd and n is odd. We proceed by contrapositive. Again, you have to tell, if you're going to prove something by contrapositive, you have to tell the reader that, otherwise they could get confused. Now here we see that the contrapositive is if m is even or n is even, then the product is even. But notice that in the product, m and n play the same role in some sense. Like if m is even and I do a proof, you could do this by cases, right? You could say, okay, assume m is even, do a proof. Then assume n is even, do another proof. But notice that m and n don't really play a different role in the product. It's completely commutative, and so there would be no difference in the proof when you assume m is even versus the proof when you assume n is even. And so instead, we do this thing in mathematics that's called without loss of generality. And I'm going to show you how to do this, but I just want to warn you that this is the most common mistake that students will make in writing proofs is use without loss of generality somewhere where they can't use it. So you do have to be very careful when using without loss of generality. Oftentimes, we use this when there's technically cases involved in the proof, but the cases are basically identical. And so, but again, students will use this sometimes when the cases are not identical and they get themselves in trouble. So I just want to make a emphasis here that you have to be careful when using without loss of generality, okay? But we can use it here. So without loss of generality, we may assume that m is even, meaning we need to assume m is even and then assume n is even, but we're only going to do one of them because it's the same for both. So that's what this sentence is communicating. So by definition 2.2, there exists a integer so that m is equal to 2 times k. Then m times n is equal to 2k times n, which of course is like 2 times k times m. And since k times n is an integer, we know that m times n is even by this definition that we use over and over again. Hence, and again, notice if you would do this, let's say you did do both cases, right? You say, okay, now assume n is even. So n's equal to 2 times k, and you would do basically exactly the same thing. So that's why this without loss of generality was used here to say, okay, we don't need to show exactly the same thing again. It's basically a repetition. And so, but now we just want to remind the reader that we've done both, right? So if m or n is even, then m times n is even. And by the contrapositive, the original statement, or let's say the original implication, is also true. Good. So again, here we see using the contrapositive, but also using without loss of generality here in the case where there's an or in the statement, but both parts of the or are basically the same in the conclusion that we're trying to draw.